gets multiplied up. Plus the multipliers can add their own additive phase noise, and so all of this can contribute to impairments in your system. So with this phase noise model, we can specify the frequency offset and dBc per hertz at each frequency offset. So at 100 hertz, we're set at a pretty ideal minus 170 dBm per hertz. Let's remove the 1 so that we're at 70 dBc per hertz.
That's almost KTV.
Yes, it's fairly ideal. And at a kilohertz, let's make that 80 dBc per hertz. And at 10 kilohertz, let's make that minus 85 dBc per hertz. And let's go ahead and simulate. And I'm going to throw out a little bit of a trick question. And I'm going to throw it out to you guys. And then if I don't get a response, I'm going to pass it to Randy to kind of keep it interesting. So normally when we look at phase noise, we would expect to have some sort of angular rotation on the constellation, right? So you expect to have some sort of phase rotation in the constellation. That can be true, but this is an OFDM signal, and clearly we've added some phase noise. We see a little bit of rotation, but in general we see some dispersion on the constellation. This may or may not be expected depending on what your familiarity is with OFDM. But can anyone explain why we're seeing dispersion instead of angular distortion? This is a pretty tough question. I hope Randy knows the answer to it.
Oh, would you like to know?
Anyone? Okay, Randy.
Right. So I have to confess, I may not know the answer. I did not expect this. This did not come up during our training session, our little dry run. I would say the multiple subcarriers is at play. One carrier would definitely see the dispersion. It depends what you're going to look at on the constellation. What are you displaying in terms of each individual subcarrier?
I'm just looking at the composite EVM.
Because I would think, you don't use like I would get two subcarriers.
Right.
You want to get 48 and the other 40 would don't pay attention to.
Right.
It's coming to play in this simulation.
And I think that, and we'll probably want to double check this, but I think also when you have multiple subcarriers, you can worry about intersymbol, intercarrier interference, right? So phase noise can be degradation to inter-carrier interference that you might have in an OFDM type of system. Whereas when you have a single carrier system, if this was just a vanilla QAM or a QBSK 16 QAM, 64 QAM type of waveform, there we would pretty clearly see some angular rotation.
You know, the same cells in the interval that is chopped down from the 400 that might be symbol.
Okay, right.
Even though it's supposed to be orthogonal.
Right. So, I mean, so the takeaway is, depending on the type of system that you're designing, these impairments may impact your system performance differently. So let's remove phase noise. I'm going to, again, make these fairly ideal, drop them back down, so they are no longer contributing. And we have this amplifier that is effectively short-circuited, so I'm going to re-enable it. So now the X is gone, which means it's part of the simulation path. You'll notice that I have a 1 dB compression point assigned to this, some arbitrary 1 dB compression point of 18 dBm and some arbitrary gain. Let's go ahead and simulate it, and let's see how the amplifier affects it. And I think this is probably pretty intuitive to most of you. Typically in a transmitter chain, the PA is one of kind of the dominant contributors to the transmitter EVM, because in a transmitter design, the PA would typically get driven pretty hard to kind of optimize efficiency, get power out, but at the same time, that gain compression is going to result in EVM degradation. So we see this here with constellation. Again, we see some dispersion. You'll notice that we see some spectral regrowth on the spectrum. So there's the amplifier is compressing. As a result of it compressing, there's some out-of-band spectral regrowth that is starting to happen. If we were doing some sort of ACPR, ACLR measurement, we would see that in terms of the number that we're measuring for the adjacent channel. And you notice that the EVM is 2.2% instead of our baseline of 0.5%. How many of you guys are familiar with something called CCDF, complementary cumulative distribution function? Okay, a couple of you. So I think everyone's familiar with peak to average ratio, PRPR. A CCDF is kind of similar in that regard, in that, a lot of these signals today are very complex, FDM signals. And so they can have high peak to average occurrences that happen at certain points of time. And so a CCDF curve gives us kind of a statistical measure of how high the peaks to get, let's say 1% of the time versus 10% of the time versus 50% of the time. And so we can see that this gray curve is Gaussian noise. We can see that because the amplifier is starting to compress, we can see the compression here. So the CCDF going into the amp is different than the CCDF coming out of the amp because now the amplifier is compressing that signal, basically clipping that signal. So let's make this a little bit more exaggerated. And we can do that by either increasing the gain or a fixed 1 dB compression point, or alternatively, let's lower the 1 dB compression point. So I'm lowering it from 18 dBm to 16 dBm. And let's just wait for the simulation to come up. Okay, so here we have our new simulation result. Now you can kind of really clearly see that there's out-of-band spectral regrowth. So this is, if we're doing an out-of-band measurement, it would probably be ACPR, ACLR, where we're integrating the out-of-band power and comparing it to the in-channel power. And because the amplifier is compressing, there is a lot more out-of-band power. We also see that the EVM has jumped up to 3.7%. EVM is kind of an in-band measurement. So in band, we're also getting more distortion that is occurring as a result of the amplifier compressing harder. And then now, if you look at the CCDF curve, you can clearly see that at the output of the amplifier, it's clipped the output signal. So, for high peak average inputs, it's basically clipping it and kind of fixing it to, have a kind of a compressed waveform. So we can continue this and kind of add all different types of impairments. Typically, the way customers would use system view is they would put together transmitter, receiver designs. They'd start adding impairments. They kind of massage things to try to get a feel for the system performance and what is limiting the system performance. And then from this, they could derive design requirements for components like filters, amplifiers, mixers, the yellow chains, and so on. And that's on the R side. On the baseband side, you could also add baseband impairments like fixed point FIRs and that sort of thing. And so as a system engineer, you can kind of trade off baseband versus RF requirements to kind of meet your end-to-end system designs. Any questions before I wrap up here? Okay.
I have a question.
I have an answer.
You probably won't for this one.
Question.
Do you have models for real components at system view?
Real components.
Yeah,
Like,
an amplifier or transistor.
yeah, so we have models. These are called parametric models where you can set parameters. I was just showing some customers, like for example, for A to D converters, we have analog devices models in here, where you basically drop in an A to D converter, you click on a list, and it includes a list of actual part numbers that are A to D converters from ADI. And so you can kind of mix and match between components like that versus ones where you might set parameters, as I have for these simulations. There are many different simulation sources and receivers. There's basically libraries. So there's 3G, 4G libraries. What we're showing on the floor is a pre-5G library that is designed to the Verizon spec. And then we're showing a pre-5G DMOD with this VSA software, again designed to the Verizon spec. And that's what we're showing for the OTA phase array demo that Randy and I are doing. Okay, so thank you for your time, and let's pass it back to Randy.
Yes, it will be time to wrap up now, it seems. All right, so, okay, so it's like nearly 5 o'clock, yes? Yes. And I found myself with 400 slides I still have to get through. So now I will quickly summarize some important things here, and then we can answer questions if you guys want to stick around and do that. Why is it doing this? I was not expecting that, but I will put the slideshow on. How about now? Okay. So let me cover one little other topic. So there's a couple topics we will skip in the interest of time, but they will be in the handouts you can download from the IMS website. So just to sort of build off of what Greg was doing with the LO, consider what is the modulation type for 802.11ad, one of the common things used at mmWave. So the modulation type is either single carrier or OFDM with a subcarrier spacing of about 5 megahertz. Now compare and contrast that to LTE, which is done at sub 6 gigahertz. That uses also OFDM, but has as a subcarrier spacing of 15 kilohertz, so it's much narrower. So the thing that I'm getting to is that, as we kind of mentioned earlier, phase noise is important. For the higher frequencies where OFDM is used, the subcarrier spacing is a bit wider, so the close-in phase noise might not be so much of an issue. But where we have modulation, where the subcarrier spacing is closer, definitely the close-in phase noise will become very important. So here's a little question. So this is like a thing you would be faced with when you go to keysight.com, and you will find a wide array of different equipment, and you're going to wonder, now which one is the one that I should use? So here we go. I've plotted here on a single graph the phase noise performance of 3 of our signal generators. So you see them here, the PSG, which is kind of one of our highest performance signal generators. We have something called the EXG and the MXG. And they all have slightly different phase noise characteristics. So we have some that have better close-in, some better in the mid-range, and then different far-out phase noise performance. So the question is, if I was using an LO with a mixer, right, to mix a signal up to mmWave, which is a common technique to go to higher frequencies. I have an IF signal and an LO. I mix those together in a mixer to go to a higher frequency. The question is, which of these sources would make the best LO for a wide bandwidth system? And I've already given you sort of the answer here, but you can see a couple of things. So this line represents the phase noise up to 1 megahertz. So all of this spectrum, this is 1 hertz to 1 megahertz, and this is a logarithmic scale, of course, and then from 1 megahertz all the way to 2 gigahertz. So if I was doing something really wide bandwidth, it's the far out phase noise that's going to definitely be important, because you have all of this integrated noise going into the system. This close-in phase noise could be a problem, so like LTE, 15 kilohertz is somewhere over here. For 802.11ad, the subcarrier spacing was 5 megahertz, so it was over here. So you can see that the close-in could be important for some applications, but the majority of the overall broadband noise is being contributed between here and here. But when people look at a phase noise plot, they often think about this, but this is all very close in relative to the overall scheme of things. So just as an example, I said, okay, let's make some measurements just to see what the results look like. So here I have a system. This is my test configuration, where I have a QPSK signal that I'm generating out of a baseband generator. I'm upconverting that to an IF with the PSG. I'm using one of 3 different LOs here, the PSG, MXG, or EXG, and I'm feeding that into this gray box, which is basically an upconverter, and then I'm measuring that at 60 gigahertz with one of our scopes. So here you can see when I use the PSG on that QPSK signal that has, I think this had a bandwidth of 2 gigahertz, I had an EVM of about 1.8%. If I use the MXG and EXG, they both had an EVM of 2.1%. So that is it's a small difference, but nonetheless a difference. If you have all of these things in a system, all of these errors add up. And if you're absolutely looking for the best overall performance, some of these little things can make the difference. So if I go back a slide, you see here the EXG, which is this purple line, and the MXG and PSG, these are the yellow and blue lines. In this mid-range, they're very different, but at the far out offsets, the EXG and MXG are actually have the same broadband noise floor. It's the PSG has an overall lower broadband noise floor, and all of this integrated noise is the thing making a difference because we were using signals that were 2 gigahertz wide. Okay, so there you go. Now you're a little smarter when it comes to determining what is the best LO you should choose when putting together one of these wide bandwidth high frequency systems. I think with that I should stop with the number of topics. There are 1,000 other things we could talk about, which we sort of ran out of time due to the complexity of the things at millimeter waves. So with that, let me wrap up with this. Let me skip that. So here we go. So a couple of things, right? So it's important to start with good cables and adapters. These are sort of fundamental building blocks in your system. If you have one of these that is bad, everything else is going to be bad. And even if it looks like it's good, doesn't necessarily mean that it's good. It's important to optimize the drive levels everywhere along the system to ensure you have the best overall signal-to-noise ratio, that you're not over-dragging things or under-dragging things. Usually you want to connect all of your frequency references together in the test system. You want to utilize IQ calibration when available in your systems. A lot of the test equipment has automated calibration routines that you can run from time to time. You don't have to run them all the time, but most of these are largely temperature dependent. So if you're here in Hawaii and you do a calibration, everything seems like it's working well, then you travel to the North Pole and turn it on, it may need to be recalibrated. So occasionally doing that is not a bad thing. And a couple other little details that I'll skip that are in the slides you can read at your leisure. Okay, so if you want to learn more, we have at the Keysight booth downstairs under the big Keysight banner a system that we put together, a 5G microwave testbed for design validation. So we have here a microwave source that we're using to generate a wide bandwidth 800 megahertz pre-5G signal and a corresponding analyzer. We have this hooked up to a phased array antenna, several different phased array antennas where we can steer the beam electrically, and also mechanically we can scan that, and we make measurements with the signal analyzer, and you can see here we're making three-dimensional beam pattern plots. And one of the things that Malcolm touched on, which is very important, people often want to make antenna measurements, and they use CW signals, but with these wide bandwidth signals, the modulation changes the beam pattern characteristics. So what you would measure with CW and what you would measure with a modulated signal over those wide bandwidths can be different. And so we can plot that here, and you can see that. It's hard to see, but there's a little beam pattern there. And this one below that is a plot of the EVM. So it looks similar to the top one, and largely in this case the EVM is a function of where that beam was pointed. But you could say, for example, what if I had a beam that was bouncing off something and coming back in, I could have multipath and multiple signals arriving at the same time. So even though maybe the power was high, the multipath could be destroying the EVM. So there's other effects that are important to investigate. So now we can make all these parametric measurements as a function of the device orientation or the device beam angle. So anyways, this is downstairs, and if you want to see a demo of that, you can swing by and check that out. And then the last slide, if you want to have, get more information, we have a variety of resources available, webcasts, app notes that can be accessed through keysight.com. And with that, we can entertain any questions you might have, or you might not have any. Going once?
Just a quick one.
Yes.
So, one of those last points you made about the antenna pattern measurements being different for modulated signals. If you were to dial up a large number of CW test tones one by one and measure the pattern at each of those individual frequencies, would you end up with the same composite sort of radiation pattern that you would with a modulated signal? Or is it something more subtle than that?
Well, I think it would be a function of the offset from the center frequency, right? So you have some bandwidth. So I would imagine if you took a number of tones over that same bandwidth, you would get a similar pattern. Or if you took a single tone and stepped it over the bandwidth and made a number of different measurements and put them together, you would probably get the same answer. If it's linear.
Yeah, that's kind of what I was getting at, I think, was that at different frequencies, the radiation pattern will be slightly different just because of the propagation phase array itself.
Right.
Unless there's some nonlinear mechanism at play.
Right. But this is the beauty of having now the ability to, to have these tools available so you can investigate those effects. How much is it causing a problem? Is it causing a problem? Maybe it's causing a little problem, but it's not significant enough to worry about, or you can see some anomalies in there. I wasn't aware that was occurring, but now I can investigate what might be the source of that. And you can see when you look at the EVM plot, it does kind of match up against the measured power, but not always. You can see some discrepancies in there. And a lot of that might be due to things like multipath. And they're set up downstairs, it's all done over the air, and it's not a controlled environment. You normally do that in a chamber, but in the real world, this is the kind of thing you'd have. You'd have signals being radiated out into the open and reflecting off of different things and arriving back at the antenna. And okay, maybe there's a lot of power there, but it doesn't mean it's all good power. Let's say it that way. Okay, anyone else? And we'll wrap it up. Thanks for attending. And